I'm very happy to have you here, Chris. So it's yours.
Great, thank you for the introduction. I'm going to do something similar where I first go over some of like the background for PRISMS-Fatigue. But before I do that, Reza, I wanted to ask if is the size here, is the display of my virtual machine, is this readable, or do you think I should zoom in a little bit here?
It's readable for me, and I have like reading this through a laptop. If I think it's fine. Yeah,
Okay.
I think it's fine.
Okay, perfect. Thank you. Great. Well, welcome everyone. So in this session, I'm going to go through our toolkit called PRISMS-Fatigue. So I'll talk through the motivation behind this this framework. I'll talk through the individual Python scripts. So these are a series of pre and post processing scripts we developed to analyze fatigue in polycrystals. And then I'll actually go through some examples of generating microstructure data, as well as simulating microstructure, not simulating, post-processing microstructure data. And all the results files that we'll deal with were actually simulated with PRISMS plasticity. If you have any questions throughout this training session, just please post it in the chat and I'll get to it. I'll periodically look over and check the questions. So to start off with, what is PRISMS-Fatigue? PRISMS-Fatigue is an open source toolkit that was developed as a partnership between the University of Michigan and the Georgia Institute of Technology. We had a lot of internal workflows at Georgia Tech and University of Michigan, specifically the PRISM Center obviously has very highly developed simulation suites. So we wanted to package these into an open source toolkit for users for fatigue. So we've just heard a lot about PRISM's plasticity. This is the crystal plasticity FEM engine that we use for PRISM's fatigue. And PRISM's fatigue is comprised of these modules here. So I'll talk through each one in detail. Generate microstructures.py, as the name implies, that Python script calls the open source Dream3D software, and it generates microstructures that vary in some type of attribute, right? So you can make microstructure instantiations with different grain size or grain shape or crystallographic texture, whatever you could specify in Dream3D. And this Python all the input files we need for PRISM's plasticity. So once we perform these simulations, I think Reza is going to go over this in more depth tomorrow. I'll touch on it today. But once we have all our outputs, so once we have the output of every voxel, we use the next module, which is called calculate fips.py. And what this does is it reads in the response of every voxel in your simulation and computes some type of fatigue indicator parameter or FIP. And I'll talk about FIPS in just a second, but to summarize, FIPS are surrogate measures for the driving force for fatigue crack formation that are often used in these types of simulations that want to assess fatigue resistance of microstructure models. After we compute these FIPS at every point in our microstructure models, we need to perform a volume averaging. And I'll talk about the various schemes that we have and why we need to volume average. And the next script after that is called compile and plot fips.py. And as the name suggests there, this script will read in and allow users to visualize their FIPS in different manners. A final script that we have available in PRISMS-Fatigue is called gammaplane.py. So this is a more complicated script, and it actually allows the user to consider different multi-axial states of strain. I'm not sure if we'll have time to get into the final script in this training session, but I do want to mention that we have a series of training tutorials, of video tutorials on YouTube for each one of these modules, and I think collectively they are 3.5 hours long. So it's very extensively documented online if you would like to learn more. So let's start with how we make these microstructures. I think Reza might have touched upon this a little bit in the previous training session, but to summarize, we generate digital microstructure models in Dream3D, which is an open source software. And what's nice about the software is that it's very versatile. So In PRISMS-Fatigue, I will open up the GUI to demonstrate some uses of Dream3D, but I will not actually generate microstructures through the GUI, through the graphical user interface. And instead, I'm going to generate microstructures entirely from the Python script. So Dream3D can let you generate microstructures of different grain shapes and sizes, as well as different crystallographic textures. So here I'm showing the orientation, distribution, function pole figures for 3 common textures of FCC materials. But what's nice about Dream3D is that you could also incorporate experimental data. And I believe Reza plans to go through this tomorrow with the users. So you can read in a raw EBSD scan and then assign the texture from that scan to your specimens. So we generate our microstructures, we perform our simulations, and then afterwards we can compute what are called FIPS, or fatigue indicator parameters. And FIPS are basically, you take some kind of response output from your simulation. Maybe it's the stress or strain or plastic strain at each voxel, and you compute some kind of measure. So what I'm showing on this slide on the far left-hand side is the Fatemi-Sosi FIP that's been shown to correlate well with transgranular fatigue crack formation, as shown in the photo there. But many different types of FIPS exist in the literature. Another common FIP is the grain boundary impingement FIP that's shown here. So this FIP considers the accumulation of plastic strain at a grain boundary, and then it also considers the stress normal to that grain boundary. Whereas in the, let me switch to a laser here. In this FIP here, what we consider in the Fatemi-Sosi FIP is the maximum plane of plastic shear strain, and then we consider the stress normal to that plane of maximum shear strain. But let me switch back to turn off the laser pointer. So we compute these FIPS at every point in our microstructure model. And as I mentioned previously, we need to perform some type of volume averaging. And that's for 2 main reasons. The first reason is that we would like to mitigate or alleviate the effects of mesh sensitivity. And the other reason for volume averaging our FIPS is that we want to reflect the physical fatigue damage process zone, because we know that fatigue cracks form over a physical volume and not necessarily at a material point. The reason we could use these FIPS as surrogate measures for the driving force for fatigue crack formation is because some previous work in our group at Georgia Tech showed a close correlation between a crystallographic version of the Fatemi-Sosi FIP and the crack tip displacement range as shown here. So this advocates the use of this FIP as a surrogate measure for the driving force for fatigue crack formation. So we compute these FIPS at every point in our model. And like I said, now we need to volume average them. And we have a few different options built into PRISMS-Fatigue for our users. The first one is to simply average the FIP computed at every element over the entire grain. So in this picture, grains are shown in different colors. But the issue with this is that the grains will vary in number of elements. So if you compare the FIP averaged over a large grain and a small grain, that may not give you a good comparison because they're simply averaged over different volumes. Plus, if your grain has a lot of elements, that means you may too intensely smear the extreme value FIP in a certain part of the grain. A more sophisticated approach would be to first separate the elements of a grain into bands that lie parallel to crystallographic slit planes. And what we can do here is we can compute this crystallographic version of the Fatemi-Sosi FIP shown in the bottom here. So now what this would consider is it would consider the plastic shear strain range on a particular slip system. And it would also consider the stress normal to that slip plane. And then we could average FIPS over these bands. So now we have a more regularized averaging volume. However, the bands will still vary in number of elements. So this is much better, but it's still not ideal. But you could take this one step further. So what we do in PRISMS-Fatigue is we have a third option for users for volume averaging, and that is over these subband regions. So you can basically further separate the band into subband regions, and then you can average FIPS over these regions, and this gives you a regularized averaging volume. So like I said, these three options for volume averaging are available to users, and I'll demonstrate all three in this tutorial. Now, after we compute our FIPS, there are a handful of different ways to visualize them, in addition to just looking at the distribution of FIPS on a microstructure instantiation in a pair view. So in PRISMS-Fatigue, the compile and FIPS.py module allows the user to fit FIPS to either the Gumbel or the Fichet extreme value distribution. So what I'm showing here is the equation for the Gumbel. And what we do is we actually plot it in a linearized fashion. So these units on the y-axis are going to look a little bit weird, but the reason we do this is if we plot the data and it appears in a straight line, that means that we are confident that it is in fact from an extreme value distribution. And there are a couple of different ways to estimate the probability, and this is one method shown in the equation here at the bottom. So in PRISMS-Fatigue, what we typically do is we simulate one or a series of microstructure instantiations. We then extract the value at every voxel. We compute the FIP. We average the FIPS over subband regions, and then we can fit the highest 100 or 50 or some number of the highest FIPS to one of these extreme value distributions. And this plot is going to look like this here. So this particular figure, this is from a microstructure model from our initial publication for PRISMS-Fatigue fit to the linearized Gumbel extreme value distribution. And you can see that it nicely displays a straight line, giving us confidence that the FIPS are in fact from the FIPS do in fact follow an extreme value distribution. In terms of that final script that I don't think I'll have time to go over, this is a script where users can simulate different multi-axial states of strain. So obviously, a lot of fatigue tests are done in uniaxial strain, but we know that components don't always, if rarely, undergo uniaxial state of strain. They likely experience some combination of biaxial and shear strain. And what we did in this module is we saw that we can generate something called a gamma plane computationally. So on the bottom left, I'm showing an experimental gamma plane. And what you see here in the curves, these are iso-life curves for one material. So this was generated by Brown and Miller in the 70s. And what they essentially did was they took a material and they tested it at different states of strain and different strain amplitudes. And then using the experimental using the experimental fatigue life, they were able to generate these iso-life contours. So this would be especially useful for a component design engineer that knows that he has some combination of perhaps biaxial or uniaxial or shear strain. And what we were able to demonstrate in that module is that we can generate a series of microstructure instantiations, in this case for aluminum alloy 7075. We can simulate them under different strain states and amplitudes. We can then extract some number of the highest FIPS, and using a Gaussian process model, we can generate iso-FIP contours. So while this isn't the same thing as life, the FIPS can certainly be calibrated to get an experimental fatigue life. And what's nice about this is you can see that these curves are especially similar. So this gives us confidence that our framework and especially the physics that we simulate is on the right track. So with that in place, I'm going to switch over to the virtual machine, and we can get into looking at how we can start to generate these microstructure models. So in this virtual machine, everyone should have fatigue as a folder alongside plasticity. So this is something new we did this year. Instead of making everyone download, different packages, we just have this virtual machine that has all the tools for all the training sessions. So in the fatigue folder, We have a series of other folders, and we will go into the source folder. And this is where we will have not only our 5 Python scripts that comprise PRISMS-Fatigue, we also have this .json file, as well as these .dreamy3d files. So before I jump into the Python scripts, I'm going to quickly go over Dream3D and essentially how it's used. So if we want to open up the GUI, the graphical user interface for Dream3D, we need to go back to the tools folder, and we will see that there is a folder called Dream3D, and this version is version 6.5.141. So this is the version that we're going to open up. If we double click and enter that folder, we have a series of other folders, and we need to go into the bin folder, and we have this .dream3d application. So if we double click on this, this will open up the Dream3D GUI. And this is what the software looks like. So there are a lot of different windows here in Dream3D. The way Dream3D works is if in this window here that says pipeline on the left-hand side, this is where your filters are going to be, and every filter is going to do something specific. Let's go to the bookmarks tab here on the right-hand side, and Dream3D has a series of pre-built pipelines. So please navigate to, if you hit the triangle here, we're going to go into the pre-built pipelines folder, then into workshop, and then into synthetic. So once again, that is on the right-hand side of the screen. Under bookmarks, please go to pre-built pipelines, workshop, and then synthetic. And we will double click on the single cubic phased equiax. So this is a pre-built pipeline by Dream3D that basically generates a synthetic microstructure model. So this is not the exact workflow that we will use, but I just want to quickly, really quickly demonstrate how this software works. So once we open that pipeline, we have a series of filters here on the left-hand side, and every filter does something specific. Every filter also has a lot of options. I honestly don't have time to go in depth to each one of these filters, but in my video tutorial series on YouTube, I do go in depth into each one of these folders. But this is going to work the same for PRISMS-Fatigue for the Python script that we will execute. So I'll go briefly over each one of these filters. In stats generator, as the name would imply, this is where we generate the statistics of the microstructure models we want to generate. So here we specify the distribution of size, and you see here that grain size follows a log normal distribution. So by changing these numbers around, we can basically change the grain size that we want for our microstructure model. We can also change the shape. So if we want an equiax microstructure model or something that is rolled, we can set that here. We can also set the orientation distribution function or misorientation distribution function if we want to specify a strong texture. So this first filter generates just the statistics. The next filter, called initialize synthetic volume, as the name implies, will generate for you an empty volume of space into which we will pack and tessellate our grains. And in this filter, you specify the number of voxels in X, Y, and Z, and you specify the resolution or the size of each voxel, as well as the origin. Now, what's important to note here is that Dream3D has no internal units of length. So by having 0.5 here in the resolution, this could be microns or millimeters or kilometers. It really doesn't matter. All Dream3D knows is that the resolution is 0.5. So if my grain size is, if the average grain size is 100, we're going to assume that this is 100 microns and that this is also 100 or 0.5 microns. So it's never going to list for you what the size is. You just have to keep track of the resolution that you state in this filter here. In the next filter, we have to specify that our grains are ellipsoidal in shape. I usually never change this in any of the work that I'm doing. The only time I think you would change this is to change this to cylinder A, B, or C. And I think if you do this, this would be if you were trying to make something like a carbon fiber type of microstructure, where you know that your features will be cylinders, so like individual strands of carbon fiber. But for grains, we keep this as an ellipsoid for the shape type. The fourth filter then goes through our synthetic volume that we instantiated, and it starts to randomly seed different centers for each of the grains, and then it grows the grains. Let's see here. Going back to initialize synthetic volume, this is a nice feature here. There's a checkbox at the top that will estimate for you the number of grains that will likely end up in this microstructure model, given the grain size distribution you specify in filter 1. So here we see that the mean grain size is around 120 microns. So this, given the dimensions and resolution here, this will give me only 2 grains in my synthetic microstructure. So I'm just going to change this to something random. Let's say 3. Let's see, 3.5. So 3.5 value of mu gives me an equivalent spherical diameter of 35 microns. And if we go back on this filter here, now this changed to 7. And if you change the resolution to be a bit smaller, so now I have a resolution of 1 instead of 0.5, that changed my estimated number of features. So this will then make our microstructure model. These other filters here, this one basically goes through each of your grains and finds out, it computes information about the neighboring grains for a given grain. So in this case, it will get for you the number of neighbors. It will get for you the list of neighbors for each grain. Filter 6 will then make sure that your microstructure has the specified crystallographic texture, and that's specified by the orientation distribution function tab here. And finally, the last filter, write.dream3d file. This will save everything that you've done into a .dream3d data file, and the format here is actually the same as a .hdf5. So we have our filters here. On the right-hand side, we have our data structure. So this is nice because it tells you exactly what kind of data you're generating, what size it is, whether it's a float or an integer. In terms of your filter list, so I can go here, and once you're more experienced in Dream3D, you can basically drag and drop and add different types of filters here. And you can see that they have a ton of filters here. And to be honest, I've been using this software. I've been using Dream3D for about 3 or 4 years now. And you can make some really, really cool microstructures. You can process data in a very advanced way, but there is a big learning curve. But that being said, there's many, many things you can do with this software. As you drag filters here, they will show up in red if they need some kind of input or if something's wrong. So if it's not expecting if you're not giving it the right data, it's gonna go red and give you a problem here. So this is a generic pipeline that I pulled up, but we have a specific one for PRISMS-Fatigue that users can change once they become more experienced. So for the quick sake of demonstration, let's open up the pipeline for PRISMS-Fatigue. So to do this, click on a file, then click on open, and Dream3D pipelines are saved in the .json format. So let's go to file and then open, and then let's navigate to the Prisms tools/tools folder. We'll then go to fatigue, source, and here we have a .json pipeline. So I'm going to demonstrate that just once more for the users. Let's go to file, open, and then like I said, we're going to navigate to our tools folder, then to fatigue, then to source, and we'll select our JSON pipeline. So this is called Dream3D microstructure pipeline.json. And if we open this, we will see that this is actually a much more complicated pipeline. So the main things I want to point to is that there are a lot of things you can change here. But the way I wrote PRISMS-Fatigue is we have a Python script that actually can edit this JSON file and tweak these parameters. With that being said, let's navigate to the fatigue folder. So to summarize, I went through Dream3D GUI, and now I wanted to start to go through some of the files we have in our source folder. I just showed you that you can visualize the JSON folder, the JSON pipeline in Dream3D, but the .json file is actually just a text file. So let's right-click on this JSON file and click on Open with a text editor. As you see here, the JSON file is nothing but a text file. And this text file specifies all the filters in Dream3D as well as their settings. And what's nice about this is that because the JSON file is nothing but a text file, we can change it in Python. And that's exactly what we do. And to demonstrate that, let's open our first pipeline, our first module for PRISMS-Fatigue, which is the generate microstructures.py. So please open this in the text editor, and I will go through the functions and the structure of the code, and then we'll go ahead and we'll execute this script. So this script has a main function that will be executed when you call the code. And the main function is listed at the very bottom. The main function also lists all the different parameters that you will specify as the user. And I've really tried to do as best of a job as I can and put as much comment as I can to each one of these options here. I will mention that at the top of this script, I have many functions, and many of those functions do have a lot of comments. Unless something breaks, unless you have an error message, or unless you actually want to make significant changes to the code, I would not change anything in the other functions. So let's just focus on this main function here. So I'm going to talk through each one of the options, and then I'll talk through how we can actually execute this script. So the first thing that we will want to change is this directory variable. And all this variable specifies is when you run the generate microstructures.py script, where should all your microstructure files be stored? And in this case, what this will do is it will make a new folder called tutorial in our fatigue folder, right? So that's right here. And it will put all the microstructure files in here. In this case, if I run the script as is, it will make this folder called test_run_2. The next file that we specify is the Dream3D input file. By input file, what I mean is in the source folder, I showed you that we have a series of .dream3d files. So these are additional files read by Dream3D that specifies the grain shape and the crystallographic texture. And I left 6 of these in the folder as starting points for our users. So the one that we will not change here is going to be called aluminum 7075 random texture equiax grains. Pretty straightforward. It's going to have random crystallographic texture, and the grains will be equiax or spherical. This next variable, this is for the banding process. So what this does is, if you recall back to when I talked about the different volume averaging schemes, that variable controls how thick these bands should be. They're usually 1 to 2 elements in width. So for the sake of demonstration, please do not change that. The next thing we can specify is our JSON path for our Dream3D pipeline. I could have wrote this so the code just looks for the file with the .json extension. However, if I do it in this fashion, then you can make a lot of different pipelines, and then you could just point to a different pipeline if you want as the user. The next thing that we specify is the executable location for the Dream3D software. So this is nothing but the location of where the Dream3D executional file is located. The next 3 variables are going to be the most important for users to change. So this will specify the size, the shape, and the number of microstructures you want to generate. In this case, the convention that I'm using is millimeters, and I'm saying that this is going to be my size of my microstructure models in millimeters, and this is going to be the number of voxels in the X, Y, and Z directions. And finally, of course, this just specifies how many microstructures I want to generate. This number here, numvox percentage, this specifies the volume of the subband regions for your volume averaging. So the subbands would be these regions here highlighted in blue. By setting it as 0.1, I'm saying that I want these subband regions to be around 10% of the total volume of each grain after I go through the code. So that is something that users have a lot of flexibility in. We can ignore these options here for the time being. We can leave this as true. If create subbands is set to false, then as you can guess, the code will not create the subbands. It is a time-consuming execution, so we're going to leave this as true for now because we're only going to generate a few microstructure models. And finally, we can specify our boundary conditions for our faces. This is important for the type of simulations we want to perform. As Reza has mentioned, we can perform simulations that are fully periodic in all 3 directions, or we can perform a simulation that is periodic in two directions with the free surface in the 3rd. That would be similar to a thin film boundary condition. And finally, we can perform simulations with no periodic boundaries. And this is important because Dream3D can generate microstructures that are periodic or non-periodic. So this checkbox here in the filter pack primary phases will control that. So don't feel the need to go to your GUI for Dream3D. I just wanted to show you that this is a checkbox that's set here, but the Python script here will control that for you by simply changing these variables here. The very last thing that users would change in this script is generate new microstructure files. So right now this is set to true. Once I run this script, it will make microstructure instantiations for me, and it will store them in this folder here. in the first folder, in the first variable called directory that we specified. Now, if I run the same script again a second time, it will overwrite everything in that folder. So I put in this feature where if you set this variable to false, it will process the data, but it will not override. It will not overwrite and generate new microstructure files. So I think we're ready to execute this file, this script now. So all you should need to change is please change the directory to look like this here. I honestly can't remember if after I downloaded this virtual machine, if I had to change this, but I'm going to drop these in the chat box. So if your generate microstructures.py script does not say this, just please copy and paste it into the lines. I think I may have changed this, so that's why I'm going to drop that in the window for you. I know I did not change this. And I'm just going to drop these as well. So please only change this if it's different than what I'm showing. But this will be easier for you to change it in the code as opposed to trying to write it down. So once again, we are going to ensure that the 4 variables I just dropped in the chat box are what you're seeing on my screen here. And this should be ready to go. If you do make any changes, make sure to click save. And now we can execute this script. So the way we will do this is we will open up a terminal shown in the bottom left-hand side here. And this looks like so. And now I will navigate to the location of the generate microstructures.py script. Excuse me. So let's go to change directory, tools, and then if you do ls, that will show you all your folders here. So then we do cd fatigue to go to the fatigue folder, cd source, and this is where we should have our generate microstructures.py script. So now this is really simple for your users. You will just type in Python, and then you'll type in generate microstructures.py. If you just begin to type out generate and then hit tab, it will autofill for you. So now if I hit enter, I'm going to get some pop-ups. I think you could ignore that first one. The first printout you'll see is that this script is in fact generating a microstructure. Oops. So it will print for you the directory that it's in, and it will print for you the current microstructure model it is working on. So it's created the first 2. Like I showed you in this text file, we specified 5, so it's going to make 5 of these. And then it's going to perform some other post-processing. And once it makes these microstructure files, I'm going to go into the folder and we could examine all the files that it generated. So actually we can head over to that folder at this point. So let's go back to the fatigue folder and click on tutorial. And here you should now have a folder called test run 2. And what you'll notice is that there's a lot of, oops, excuse me. Let me close out of this here. You'll see these printouts here in the window, and all it's doing is it's doing some additional processing to get the files that you'll need to perform the FIP volume, averaging. And depending on the power of your computer, on how much memory and processors you allocated to the virtual machine, this might take a little bit longer, and you might hear your fans start to spin up. So at this point, this is the printout you should have received, and you should have this folder here called test run 2. I think I'll take a brief pause here, and if anyone has any questions, please feel free to drop them in the chat box. Okay, if not, then I think we could go on. So what I'll do now is I'll briefly touch on all the files that we generate. We have a series of different files, and you'll notice that there's 5 of each type because we have 5 microstructures. Let's start with visualizing the microstructures that we made. So we actually have 2 different ways to visualize these. We can open up either this XDMF file, or we can open up the VTK file. They're going to show us the same thing, but they're different. And here's what the difference is. The VTK file is nothing more than a text file that has the microstructure data, right? The XDMF file points to the .dreamy3D file. So both of these, the VTK is a separate file, whereas the XDMF is linked to the .dreamy3D file. They have the same information, except the VTK is a text file and the Dream3D is a .hdf5 file. So it's more efficient in its storage. If you're concerned about taking up too much space on your hard drive, you can turn one of these off. I like them both because sometimes in my work, I need to read in data in a certain format. So both options are there for users. Now to open this, I think the easiest way is to drag this onto the ParaView icon on your desktop of your virtual machine. So you can drag either the XDMF or the VTK. Let's drag the VTK on the ParaView file and drop it on there. And this should open up ParaView, and we can visualize one of the microstructure files that we just generated. And this is ParaView. You can click this checkbox here, so this doesn't pop up another time we open up ParaView. Let's make this a little bit bigger. And ParaView, it can be an intimidating software because there's a lot of buttons. The 2 buttons you need to know are apply. So anytime you open anything, you just want to hit apply here on the left-hand side of ParaView. And then the first thing you're going to get is the outline of whatever you just generated. So by default, you have the outline. In the top here, you will want to switch to surface. So this will show us the surface of our model. And let's take it one step further and click on surface with edges. So this is nice because now we can see the individual voxels of our microstructure. But this is showing us the microstructure as a solid color, so that's not terribly useful. So let's, instead of visualizing the solid color, on the drop down here, we can visualize 3 different things. We can visualize the Euler angles, the feature IDs, or the phases. So let's first go on Euler angles. As the name implies, this is the visualization of the orientation of each one of our grains. So each color here would indicate a different grain. By default, it lists the magnitude, which obviously doesn't make any sense. The Euler angles are obviously the 3 rotations that we can use to rotate our grain from our sample frame to our reference frame. If you click on magnitude, you can visualize the X or the Y or the Z, which basically just corresponds to the first, second, or third Euler angle. The reason ParaView gives you this option for the magnitude is because ParaView only recognizes this as a vector in 3 dimensions, right? So pair view might think, oh, this is a velocity. So it's going to give you a velocity in the X, Y, and Z, and then a magnitude of velocity, because it just doesn't know what Euler angles are. Just so that doesn't confuse you as to why that says magnitude. The next thing we can visualize are the feature IDs. So this shows the individual grains once again. And this indicates to us that we have around 240 grains in the microstructure model that we generated. To summarize, we hit apply, then we hit surface with edges or surfaces, and then we change here what we want to visualize. That's, if you're a beginner to pair view, those are the few things that you need to know. The other thing that will be useful is if you click on information, it's going to tell you the number of cells, in this case, number of voxels, the number of points. In this case, every voxel has 8 points at the corners. And it gives you the ranges for the data that you have. So we see that for feature IDs, the ranges from 1 to 244, which indicates this microstructure model has 244 grains. Since I have it open, the last thing I'll demonstrate here is that you can, like I said, there's many filters here, right? A lot of things you can do here. I'm not going to go through each one, but one that is kind of cool is this one here. So this is called a threshold. So if you click on your model here and then you click on threshold, that will be the 1, 2, 3, 4, 5, the 5th icon right above where we have our name of our VTK file. This will act as a filter on the microstructure we read in. And this is where you alter some additional things. So this is cool once you start to make more microstructure features. Let's say that you want to visualize just the microstructure, just the grains or feature IDs, as they're called in Dream 3D, with grain IDs between 1 and 10. So we could change this number here in the bottom from 244 to 10. And then if we hit apply, we have this here. So now we have just the grains with IDs 1 through 10. If we go back on the VTK file, if we click here, we see that this eye has now closed. So this, if we click over here, that's how we toggle those views on and off. And what I sometimes like to do is for this first item in the pipeline browser, let's change that from surface to outline and open the eye. And now we have something really useful is we can visualize in this microstructure model, where are those grains with a certain grain ID. So I think that's all I will say there. So let's minimize this. Let's not close out of it just for the time being. And let's go through some of these other files that we have here. The two that will be most obvious to you are the grain ID and orientations.txt files. As Reza has mentioned, these contain all the microstructure information that we need to simulate our microstructures in PRISMS plasticity. So you can already imagine what's really nice about PRISMS-Fatigue, just this first script, is that I can generate hundreds of microstructure models, and it will number all the different microstructure models automatically. Let's see what else we got here. So one other thing that's really useful is this CSV file. There will be a CSV file for every microstructure model. And if we open this up, this is basically an Excel sheet of every grain in our microstructure. And this is really useful because we have grain averaged quantities. The first box here tells us the number of grains in our microstructure. So this says 244, which is great news because that matches up to what we have visualized in pair view. And if we scroll here, we have things like aspect ratio for the shape. We have our Euler angles for the orientation. Euler angles here, Euler angles 1, 2, and 3. We have our size, so in the equivalent diameter. We have number of elements per grain. We have number of neighbors. We have whether it's a surface feature. So if surface feature is 1, that means it's at the boundary. If it's 0, it means it's deep within the model. We have the volume as well. And what we also have, so we have a row for each grain. So this should have 244. And then we have some more information. We have for grain 1, we see that the number of neighbors is 12, and we actually have the entire list of neighbors for that grain. So this is really, really useful. There should also be 244 rows of this. And then we have another chunk of information that says for grain ID number 1, it has 12 neighbors, and here is the shared surface area between that grain and all of its neighbors. So very, very, very useful. And finally, we have, I guess it's not here. There is another more data that you can generate that gives you the misorientation between neighboring grains. So I'm going to close out of that, and in the interest of time, I'm going to move on, and this will actually be related to the question that was just asked. The question was, can you please elaborate how you said a FIP can be related to fatigue life in the PowerPoint? That's a little bit more nuanced, to be honest, but if you, here, I'm going to post my email, and then you could shoot me that as an email question. Because I can point you to some literature that relates FIPS to fatigue life. It would take a little bit more than a few minutes to explain, but if you email me, I can send you a response. Let's see here. So all the other information here, all the other files, I don't have time to go into, but those files are going to give you extra information for the microstructure that we generated or that are necessary to compute our FIPS. So at this point, instead of actually simulating the microstructures that we generated, what we're actually going to do is we're going to process some previous microstructures that we simulated. So if you could please extract the files in the zip file here. So if you go into the folder called tutorial, there should be a zip file called PRISMS-Fatigue training session. And I will follow along. So if you right click on this and click on extract here, that will extract all those files. And I'll go through what this is from. And basically these are a series of microstructures that we already simulated that we're going to compute the FIPS for. We had a question, can this Python script for microstructure generation be used with other CP tools such as the mask? I think they can be. The only thing you would need to do, which I'm not sure of, is the mask will also require some kind of input files. So for the mask, I've never used it, but I imagine you need to specify, the orientation of every grain. And then for every voxel, what grain does that voxel belong to? So if you know the format of those files, which I'm sure that you do, you just need to slightly alter the files we generated, that grain ID and the orientation.txt file. Another question, are these files also uploaded on the GitHub? I don't think they're on the GitHub, but they are available on the Materials Commons, and I will give you a link for that right now. Give me just a second here. Let's see here. Just have to log in. Publish data sets, training session. So So this link I just dropped here, these have the exact same files that's in this zip file in the virtual machine. Next question, are the positions of the grain IDs random for this tutorial? If you're asking in the visualization here, if you're asking whether the grain IDs are positioned at random throughout this microstructure model, that is the case, yes. Samuel asked, what's the output you get from Prisms plasticity that you use in Prisms fatigue? That's an excellent question, and I'm going to answer that for you right now. That link did not work. Let me see here. So try this link here. That link is working for me. So if it still doesn't work, shoot me an email and we could follow up with that after the tutorial. So if we open this, okay, great, nice, that it worked, perfect. If we open up this folder here, Prisms Fatigue Training session, this actually contains the information for 3 of our cases in our publication of Prisms Fatigue. So for reference, don't feel the need to go to that link now, but this this paper I just sent the link for in the chat. That is where this data is coming from. So in that paper, we investigated the effects of a free surface on fatigue, the effects of grain morphology, as well as the effects of different crystallographic textures. So for this tutorial, we're going to click on texture effects. So please go into that folder. And you'll see here that we have 3 folders here. And these folders are called cubic equiaxed, random equiaxed, and rolled equiaxed. So the first part of that name refers to the crystallographic texture that we simulated. So if we click on random equiaxed periodic, that is going to give us a series of files, and these are very similar to what we just generated. And it's going to be the same type of information. We have a CSV file for every microstructure model that we generated. We have a grain ID.txt, and we have an orientation ID.txt. After we perform our Prisms plasticity simulations, we're going to get 3 additional text files. Now, I guess they're not, I guess it is a text file, but we have outputs from our simulations from Prisms plasticity. The first one that Reza will talk about tomorrow, I actually don't think I have it here, but that's okay. Every Prisms plasticity simulation can output a stress strain curve. I guess I did not export them in this case. So we're gonna not talk about that. But Samuel, to answer your question, the outputs that we get are these CSV files. So these CSV files, are the outputs of every voxel at the points of max tension and max compression in our simulation. So let's open up one of these and I'll show you what it looks like here. So let's open maxcomp_0. The _0, it indicates that this relates to the microstructure model that is _0 for the grain ID and the orientation. So that's how we keep track of the different results and microstructure files. If we open up this file here, we have a series of data from each voxel in the simulation. And these aren't labeled here, but the way this works is for this data, the first column is the grain ID. Next 2 columns are the X, Y, and Z centroid of every element of every voxel. And the remaining columns are some values that we exported to compute a fit. So in this case, as Rosa mentioned, we can simulate different types of materials. So everything we demonstrated in this work was computed using aluminum 7075, which has the FCC crystal structure, the face-centered cubic, which means it has 12 slip systems. And what we export here is actually the current value of plastic shear strain, subsystem 1. So each one of these columns is the current value of gamma, or the current value of the plastic shear strain for a slip system. And this would be for slip system 1 in this column. This would be for slip system 2, slip system 3, and so on. So we have this. What we also export here, starting here, this would be the stress normal to slip plane 1. Obviously, do not feel like you need to type this in. In fact, please don't modify this script. This is just, please don't modify the CSV file. This is basically, I just wanted to demonstrate what values are in each of these columns here. The reason we have these values here is because when we were formulating PRISMS-Fatigue, this is just one type of FIP that we can compute. And let me show you really quickly what FIP that is. Just a second here. Let me pull up a PDF. Just a second here. So I'm going to pull up one of my previous works that uses the same manuscript here. Just a second. So let me scroll down here. Actually, let's go to the PDF view here. So this is essentially what we're computing. So this FIP here, this is what we call the crystallographic version of the Fatemi-Socia FIP. So this considers the range in plastic shear strain across a loading cycle or a straining cycle, and then the peak stress indicated by sigma here, normal to that slit plane. So we have our microstructure models, and this is related to fatigue, right? So we cyclically strain the material. We have a maximum point of compression, and we have a max compression and a max tension point. So the reason that we have these files here called max comp and max 10, these correspond to the points in the simulation of maximum tension and maximum compression. And like I said, these CSV files contain information for every voxel. So essentially, Samuel, to wrap up your question, that is how we consider the response at every voxel in our simulation. So this is the raw output, right? It has the variable gamma and the variable sigma, but now we need to actually compute our FIP. And the way that we will do that is we will go to the calculatefips.py script and modify something there. So I'm going to open up a new folder, and we will go to the tools, fatigue, source, and we're going to open up calculatefips.py. This script also has a lot of functions at the top. You don't need to change those. All you need to change is the one at the very bottom called main. And this will look very similar to our generate microstructures.py script. I'll talk through each one of these variables because it's a relatively short list. And we're going to use this script to compute the FIP and the results that we just looked at. The first thing that we need to change is we need to change our directory variable. So copy and paste what I sent in the chat. Actually, I take that back. I think I already changed this. So I'm going to drop this in the chat box. And if it's not like this for you yet, I would like you to change this directory variable to point to that folder that we just looked at. This is how I deal with having a lot of different folders on your system. By setting just one variable here, this will tell Prisms where to look for those results CSV files. The next thing we need to specify in calculate fips.py is the shape or number of voxels in our microstructure model. 9 by 29 by 29. You might be asking yourself, why can't Prisms just read the CSV file and figure out how many voxels are there? That's certainly a possibility. I just like to keep it really simple. And you just need to make sure you keep track of this variable to make sure that the shape here matches the shape of the microstructures that you're analyzing. Number of instantiations is equal to 5. This just specifies for how many microstructure models do you want to compute your FIPS. In that folder, we actually have 30. So we could change this to 30 and calculate FIPS for all 30, but we can leave it as 5 because we just want to demonstrate this for a few microstructures. Here we specify the type of FIP that we would like to compute. And this actually controls something in the function up top. So I'm going to show you that in just a second. And these parameters here, kfip and sigma y, if you're asking yourself what this is actually this variable k and this variable sigma y. So in this FIP, we need to specify these two variables. So sigma y is the yield strength of the material. And this is done to normalize that contribution of the stress normal to the slip plane up top here. And then K also controls the influence of this entire term on the FIP that we compute. So I left this as 10 because that is historically what we've used for this material system. But this would be more important if you know that you have a fatigue life to calibrate to. And number of slips system is equal to 12. That's something that's left over from since when the code was under development. You don't need to change that unless you're working with a material system with a higher number of slip systems. Visualize FIPS. This would actually write the values of the FIPS to the VTK file associated with this microstructure model. So for this to work, we actually need to have VTK files for our microstructure models. So let me quickly check if we have those. So we do in fact have VTK files. So let's go ahead and we will set this to true. Full integration. I'm not sure if Reza has mentioned this, but Prism's plasticity can run simulations with full integration elements. So with 8 integration points per element, or reduced integration, so only a single integration point per element. And you just need to specify adequately what kind of integration was used. In terms of this if statement here for the gamma plane, we will not look at that because we will, in this tutorial, not do anything with the gamma plane. The last thing I wanted to mention with this script is this variable here called FIP type. So what's going on here? FIP type is right now set to fs_FIP. And if you go up to this first function here, this code here. So here's how users can implement their own type of FIP. In this case, we have a couple of options for FIP type, right? We can specify FS FIP, and this will actually compute the FIP that is shown here. But if we specify plastic shear strain range, this will actually not consider the second part and only consider the FIP if it was just the half of the plastic shear strain range. So you'll see here that you as the user, you can just basically add a brand new line, right? You can say if FIP is equal to custom FIP, you can, change around what you compute here. The caveat, the thing you need to know is, like for instance, one popular FIP is the strain energy density, right? And to compute that, you need the total strain and the total stress at each voxel. So you need to make sure that you change the PRISMS plasticity files to actually export your strain at every voxel and your stress at every voxel. If you do that, then those files will be in the CSV file for every microstructure. And then you can go in here and you could do, stress times strain at every voxel. But that's the big caveat here is you as the user, if you want to compute some type of FIP, then you need to know that you're actually exporting the necessary variables in your CSV file. So with that being said, okay, let's click save. Like I said, please make sure that your directory path is shown as I've indicated in the chat box. And then your shape should be, I'll drop that in the chat boxes too. Your shape should be 29 cube and number of instantiations should be 5. So now we will go back to our command window. We should still be in the source folder. And now we will run Python calculate FIPS.py. And we'll hit enter. And in this case, we did not get a printout because I did not include one for the calculated FIPS.py script. But we did not get an error. So that's a good sign. If we got an error, that would be bad. So let's go back to our random equax periodic folder. And now we see that we have these additional files here. We have prisms_fs_FIP, and we have these VTK files. So these were just generated when we called this calculated FIPS.py script. This .p file, this is a way to store information in Python. So we computed the FIP and we stored it as a .p file. We also, because we set this VTK visualize FIPS to true, we took the VTK file that was already in this folder and we basically appended to it the highest FIP for every element. So let's quickly visualize this here. So I'm going to drag this VTK file onto ParaView here. So this once again opens up ParaView. And as I said, you want to hit apply. We're going to get this outline by default. And on the dropdown, I will go to surface. And in this case, I have an additional item I can visualize, and that is the max element FIP. So if I click on that, now I have a distribution of the highest FIP for each element in the microstructure model. And you'll notice that we have this blue color, white color, and we have only this one spot here. And this kind of indicates to you already that for the FIP that you compute, it will be fairly low throughout the microstructure model and only really high in just a few locations. So this would be also a good spot to check out that threshold filter. So if we click on if we click on a threshold here, in this case, we don't want to threshold the feature IDs. We want to threshold the max element FIP. We'll click on that, and then if you hit these update boxes here, this will actually show you the lowest and the highest FIP for every element that we have. And since the highest FIP is 0.008, let's type in here 0.003. Just something to visualize the highest FIPs. So if we hit apply, okay, that's still showing us a lot of elements. Let's do 0.005. Okay, so that's more interesting here. So let's visualize all the FIPs that are at least 0.005 in magnitude. What we can do to kind of get a better sense of what's going on here is you'll notice here that we're still visualizing the grain ID or the feature ID. So we need to go up to this box, and instead of feature ID, select max element FIP. So now we can actually visualize the FIPs. And then as I did before, let's click up here where we initially had our data. And instead of surface, we're going to click on outline and then open this eye here. So once again, outline and open that eye. And I like to do that because it gives me a sense of where those elements are in the model. So these are all the elements with a FIP of at least 0.005 magnitude. I suppose if you go back and if you click on the drop down here, if you click on feature IDs, what's useful here is that then you can visualize what grain ID manifests the highest FIP and therefore the highest driving force for fatigue crack formation. So that's essentially the gist of calculating the FIPs. I'm going to stop here, and before I dive into the volume average FIPS.py, I'd be happy to answer any questions anyone might have. So feel free to post them in the chat box. Okay, if there are no questions, we'll move on. So we've generated our microstructures, we've looked at the output files, and we've computed our raw FIPS. So now we need to volume average our FIPS. As I mentioned at the start of the talk, we can average our FIPS over entire grains, or over bands, or over subbands. And I'll go through each one of these schemes and show you how it can be done. So first, let's navigate to the fatigue folder once again. So to the source folder in fatigue where we have all our scripts. And we will click on volume average FIPS.py. Once again, let's scroll to the bottom. And once again, we want to make sure that our directory, that you change the directory variable to be the same as what we had in our calculate FIPS.py script. So let's talk through the variables in this folder. First, we have our directory, which we already mentioned. The next thing we have is our number of instantiations. So that folder had 30 instantiations. We computed FIPS for only 5. So for the sake of consistency, I'm going to change this from 10 to 5. Actually, you know what? I'm going to leave it at 10 and just show you what happens if you don't change things accordingly. So this will go through the first 5 microstructure files, and then it's going to give me an error because it's going to look for the sixth one, but I never computed FIPS for the sixth microstructure model because number of instantiations was set to 5 in our previous script. So this will give me an error. I also specify here the FIP type. So I'm going to leave it as fs_FIP. And this will look for the file that has prisms_fs_FIP in our tutorial folder. So in this folder here, this is the name of the file with the FIP. And if I computed a different FIP, then this file name would be different, right? If I computed a FIP of the normal stress, then this would say prisms_normal stress. The next thing we specify is the type of averaging volume that we want. So we have the options of subband, band, or grain. And we'll actually go through each one of these. The question from Samuel is, I guess it should be possible to generate an RVE from EBSD data, perform the CP simulations, and then use the calculate FIPS.py script directly. Yeah, I mean, yeah, you can certainly do that, yeah. Yeah, so what's nice about these tools is you don't necessarily need to use all the Python scripts in sequence, right? Like if you have one microstructure file that you generated somewhere else or someone sent to you, maybe a collaborator, and you simulate with Prism's plasticity, that means you didn't use the generate microstructures.py, but you can still use the calculate FIPS.py module to calculate FIPS. Or say you're not interested in fatigue, but you want a way to easily generate many microstructures, then you can still use the generate microstructures.py script to generate your microstructures and, honestly do whatever you want with them. Okay, so I'm going to start with grain averaged FIPS and then move to band and then move to subband. Because grain averaging is the simplest, and then band and subband gets progressively more challenging and more complicated. So now that we changed the directory to point to the right place, we're going to leave number of instantiations as 10, leave the FIP type as Fatemi-So CFIP, and leave averaging type as grain. We'll go back to our command window, and I'll type in Python, and we're going to type in volume average FIPS.py and hit enter. So let's see here. And you see this executed very fast. So we saw that it said here for instantiation 0, the largest grain averaged FIP is this right here, and that is in grain 45. So for the 5 microstructure files for which we computed the FIP, it computed the grain averaged FIP, and it gave us a printout of what that FIP value is and the exact grain. And then it threw an error. It said, hey, I'm trying to volume average the FIP, but this file, Prisms FS_FIP_5 does not exist. So like I said, that's because we specified 5 here, or we specified 10 instead of 5. So if I rerun that, but I change number of instantiations to 5, then it runs, gives me the same printout, and does not throw an error. Let's look at the file that it generated here. So it generated a .p file of the grain averaged FIPS, and it generated a CSV file. So this CSV file, if we open up one of these, all this has is it has the FIP for every grain. And these FIPS are not sorted in any way. If we scroll down, we see that we have 250 FIPS, which corresponds to 250 grains. So the first row would be the highest, would be the grain averaged FIP in grain number 1. And the second row is the grain averaged FIP in grain number 2, and so on. So that is all you need to do for averaging FIPS over grains. So let's now move on to something a little more complicated, which is averaging FIPS over bands. Now, you might ask yourself how this is actually averaging these FIPS. So to average FIPS over grains, the code obviously needs to know the grain ID of every element. And that is something that I've provided in this .p file. So these files here, element underscore grain underscore sets, is a very small file, and this just contains the information of which grain ID every element belongs to. And this is generated automatically by the generate microstructures.py script. If we average FIPS over bands, then we obviously need to know for every grain, what are these bands and how are they separated? And that information is automatically generated in these files called element underscore band underscore sets. So let's go ahead and we change this to band. So let's run this again, and let's just change averaging type to band instead of grain. And as you might expect, this script is going to take a little bit longer to run because there are many bands for every grain. So for instance, in this image here, this grain has around 100 elements. So to average the FIPS over the elements is really quick, but to average over the bands, we have maybe 30 bands, maybe 35 bands. And if we have several hundred of these grains, then this is going to take a little bit longer. So I will go to my command prompt and I will once again execute Python and then click on volume average. So this wasn't as fast, but still relatively fast. And the printout in this case says highest band average FIP, location, and value. In this case, because of the way the code is set up and the fact that we're using Python, everything is indexed at 0. So we have the grain ID, and then the, I believe this is the band, and the number of elements where the highest FIP is located. But to make sure, let's look at the file that is generated by this script here. So if you sort by the date modified, this will give you the most recent file. And now we have additional CSV files. These are called band average highest per grain, the name of the FIP, and then the number of the instantiation. And if we double click on this guy, we have the information of every FIP. And in this case, our CSV file has a little bit more information. So we have here the actual band average FIP value. We have the grain ID for that FIP. We have the slip system number, and then we have the grain layer number. And then we also have the number of elements in that band. So these are all sorted in descending order. And what we have here is we have that grain 239 has the highest FIP, and this is located in slip system number 8. If I really quickly go to our printout here, what I mean here by indexing at 0 is that instead of 239 slip system 8 and layer 6, this will say 238 slip system 7 and layer number 5. The slip system number is literally for the 12 slip systems, which slip system is that? And the layer number will just help you keep track of, if you consider this this band here, you could say red is 1, this is 2, green is 3. So you can pinpoint exactly the location of where the highest FIP is when you visualize the microstructure. So this is really useful too, in terms of you can check the number of elements in each band. The reason we volume average FIPS, like I said, is because we want to regularize or mitigate the effects of mesh sensitivity. So it may be problematic if you get a really high FIP, but that's averaged over not many grains. So in this case here, this FIP, although it's not really high, the number of elements in this band is only one. And that sometimes happens based on just the geometry. But if you were to do something like this in your work, if you saw that the highest band average FIP is really high, then maybe it's averaged over only one element, which means it's really not averaged, which means you may need to do some additional processing with that microstructure. And this, the number of rows here is going to be one for every grain. So once again, we have 250. And this, this is your band average FIPS. So let's close out of this. And now we're going to the last type of averaging, which is the subband. Question, do I remove those one elements from statistics? So to be honest, in all the work that we've done, I've never really stuck with FIPS averaged over bands. I usually do it over subbands. And the reason for that is subbands will be preferred because the averaging volume is the same. And I'll demonstrate that for you in just a second. So let's change this volume average FIPS.py script, change the averaging type from band to subband. And let's go back to our command prompt and we're going to rerun this script. And now this one is actually going to take a little bit longer. So I hit enter. And granted, that was still relatively fast, but didn't take too much time. So we now have additional files. We now have something called subband averaged highest FIP per grain for FIP _0. So this CSV file will have the highest FIP for each one of the grains when we average over subbands. I'm going to open up the previous file that we had where we averaged over bands and we can compare the two. So I will have the subband information on the left, on the right, and the band average information on the left. The additional information we have when we average over subbands is the subband number. So we're getting a little more complicated now because the way I set up the code is to keep track of your grain, your slip system, your band, and then your subband. So your subband number might be, you know, which one of these is the subband that has the highest FIP. I should have said this at the start, but it's easy to band your microstructure because you could just take your grain and basically slice it into different bands along the crystallographic slip planes. For the subbands, this takes a little more work. In the generate microstructures.py script, you can specify whether you want your subbands to be a certain volume of the grain. So you could say, you know, I want my subbands to be 10% of the volume because I know from my work that that's like the that's a good damage zone over which the fatigue crack is going to form. Or you can specify a number of elements that you want your subband to be. So for this work, I specified that I want my subbands to be exactly 8 elements in size. And the way the code works is that it considers every element of a band, and then it goes through each one of those elements and its neighbors. It finds the 7 closest elements, and then it stores that, and then it makes sure that when it has the list of subbands, that it only considers unique regions. So to summarize, the subbands, the list of subbands is a unique list of adjacent elements. And that is what we have in this last column here. So we see that some bands have many subbands. And here, what's nice is that this shows you the number of elements in that subband. And we see that the subbands that have the highest volume average FIP all have 8 elements, which is really nice. There is here this guy. So this subband has only 1 element. And I think we had, if you look at the band average, it's actually the exact same value. So in this case, the highest FIP in grain 106 is the same whether you perform a band averaging or a subband averaging. What's interesting too is that you will get different values for the FIPS if you average over bands or subbands. They will be similar. So for instance, the highest FIP in the subband is 0.00. In the subband is 0.0052. In the band is 0.0047. They happen in the same grain, the same slip system, and the same layer, right? But in this case, it happens over a smaller region. So it happens over 8 elements, not the 13. So that is why, I mean, I suppose this one you'd consider to be a little bit higher because it's not as smeared, right? So if you average FIPS over more elements, that's going to drop the value more and more. Let's minimize this. And I will stop right now to take any questions from the audience, whether it's about generating microstructures or averaging FIPS or whatever questions you may have. Please feel free to ask them in the chat box. So a question we got is, does the number of subbands always fix to 8? That's up to you. You can change that. So if I go to, I pulled up the generate microstructures.py script here. And this is where you can specify that. So right now this line is uncommented. But if you uncomment out this line here, you could basically hard code, I want 8 elements for my subbands. Now, if you change the number of grains or number of elements in your model, that will not work well. And the reason for that is if this 8 elements for your subband works well, if you have around 100 elements for the whole grain. If you have 500 or 1,000 elements for your grain, then the subband is going to be really, really small and maybe too small for like the kind of physics that you're trying to model. But also the process of subbanding microstructures takes a really long time. So, you might be in trouble if you do that. But that's something that you would just need to try out and see how it works. That's why I left this commented out. Users can change that, but instead what I specified here is if you just specify num vox percentage, you could just say, I want my subbands to have a volume of around 10% of the grain. And then this will just automatically pick a number of elements based on that. And that calculation is done in this line here. Another question, can this package potentially work with Abacus? So to be honest, a lot of these workflows were initially developed to work with Abacus, especially the generate microstructures.py script. You can tweak the generate microstructures.py script and make it so it writes for you the input files for Abacus. I don't have that as a feature here, but you can certainly do it. You can also, after you perform your Abacus simulations, you can, if you can get your results file in a similar format to what I showed here, then you could use all the rest of the scripts here. So yes. My pleasure. I think we have time to do one final script, but I would have to check. So in the meantime, please feel free to ask any more questions, but I'm going to look at some other scripts I have here. Another question, can these Python scripts be obtained without the VMware? Yeah. So actually all the Python scripts are located on the GitHub page for Prisms. So I'll drop that link in the chat. And this has all the exact same Python scripts that I've gone through here. So if you could see this window here, if you go to the source folder, this has everything we just talked through actually right now. So they're all there. Since we have a little bit of time, so I don't want to go in depth through the scripts, compile and plot FIPS and gamma plane. Honestly, because those video tutorials already exist on YouTube. I'll drop those in the chat box as well, but I did want to show you some other features that we have. So let me share this really quickly for everyone. Let's see here. Share, copy. So if you click on the link I sent in the chat box as well, you'll find a lot of videos where I go through each of these scripts, so that those videos will be a nice review. In the meantime, what I did want to share here is that we have this special folder called applications on the GitHub page. Now, applications is a folder of the different demonstrations that we've done with Prisms. So they're summarized here. And what's nice is that for everything that you listed here, we actually have not only an associated publication with that work. So in this case, we studied the effects of the different boundary conditions that are available in a Prisms and their effect on fatigue. We also have a link to the materials commons where we have all the data to generate the results of the paper. So we have the raw microstructure files, we have the raw simulation files, and we have all the code necessary to reproduce all the plots. So we have one paper where we investigated the effect of boundary conditions. And here you see that I have additional Python scripts, and these Python scripts will generate all the figures in the publications. So we have a paper on that. We have another paper where we investigated the effects of sample size and gray neighborhood on the extreme value response. So in this paper, we really, I guess, made the most out of the framework by simulating very large microstructure models and investigating the FIP response. So like I said, in this folder, we have all the Python scripts necessary to generate and analyze all the unique microstructures in that paper. And in this last one here, this is our most recent paper, effects of grain shape. So this was actually not only implementing the ability to simulate grain shape in Prisms, but also seeing what effect this has on fatigue. Now I have a final script. This is called generate simple microstructures. So this is actually something that is not possible to do in Dream 3D, and you guys might find this useful. So what I wanted to do for one of my works is to generate a microstructure with a cubic grain structure. So I'm showing here an example of that. So this would be a microstructure, an artificial one with 280 grains. So it has 4 grains in the X, 10 grains in the Y, and 7 in the Z. So 4 times 7 times 10 is 280. And in this case, it has, I think, 5 by 5 by 5, so 125 elements for every grain. Now, Dream 3D is not able to generate this, but using the Python script I included here, this will write for you a text file that you can then read with this JSON file to make this type of microstructure. Now, as I said, it's not equiaxed in terms of the grains; they're not spherical, but this has uses for different types of modeling purposes. So that's something that's also available for users here. And the final thing I wanted to mention, I suppose, is this PDF that's a guide of everything I've mentioned here. So in addition to the video tutorials, this has a very detailed list of, what are the options in Dream 3D for your GUI? What are all the inputs for generate microstructures.py? What type of variables should that be? So it goes through all the scripts. It talks about banding and subbanding of your grains. It tells you, when you run a script, what is every file called that you generate. So I believe that, to summarize, on this GitHub page, our combination of the applications and tutorials here, the PDF tutorial to be specific, as well as our publications and the hours of tutorials on YouTube, I feel that it's very well documented. So I hope you guys found this useful. But I'd like to close here just to give anyone time to ask any more questions before we hit our end time here in about 10 minutes. So thank you very much for your time, and I'd be happy to chat out further.